Okay, 4.3, the remainder and factor theorem. Now we're going to draw from some of the different concepts that you learned in Algebra 2. For example, we're going to start right away with divide 2x squared plus 3x minus 8 by x minus 2. State the quotient and remainder. So we're going to do this using long division. To set the long division up, we have x minus 2, and then 2x squared plus 3x minus 8. Again, to do long division, we want to try to match the first term up with the first term that is being divided by. So to do that, we're going to multiply it by 2x. So 2x times x is 2x squared, and 2x times a negative 2 is minus 4x. And then we must subtract. So 2 minus 2 is 0, 3 plus 4, or 3 minus minus, which is a plus 4, is 7x. Bring down the minus 8. Now, what are we going to multiply that by to get 7x? That is a positive 7. So plus 7, 7 times x is 7x. 7 times negative 2 is negative 14. So negative 8 plus 14 is a positive 6. Now before, we've done this with the rational. We had some end behavior asymptotes, specifically a slant asymptote. And the quotient, which is one of the things they asked us for, was our slant asymptote before. So the quotient, q of x, is the answer, 2x plus 7. Again, which happens to be what the slant asymptote was when we did previous sections. We're also interested in the remainder. When we were talking about the slant asymptote, we had no interest in the remainder. Now we are. Remainder is 6. So again, we're just reviewing what we've done in Algebra 2, what we've talked about earlier when we studied rational functions and end behavior using long division. Now let's take a look at the second example. Find f of 2 for fx equal to 2x squared plus 3x minus 8. Okay. So we're just going to substitute 2 in for x. So everywhere you see an x, we're going to put a 2. Okay, we can put this into the calculator. 2 times 2 squared plus 3 times 2 minus 8. And we get 6. Now, if you notice how these two problems were set up, this 6 happens to be the same as this 6. That's not just a coincidence. That was set up for a very specific reason. This basically defines the remainder theorem, one of the two big concepts we're going to be studying in this section. The remainder of the first we did long division was 6. The remainder of, by plugging a 2 into the same function, we get a 6. So where does the 2 come from? What we divided by. Okay, it's also right here. Okay, we have x minus 2. So we're seeing that this is the opposite number being put into the function. That's giving us the remainder. So we can now state what the remainder theorem is. The remainder theorem says if a polynomial p of x is divided by x minus r. So it must be of the form x minus r. The remainder is a constant p of r. So as you can see, we have x minus r. The opposite of that, positive r, is what we plug in to find the remainder. So a very simple way to find the remainder. We don't know the quotient, though. All we would get is the remainder. Okay, but when it comes down to breaking down larger polynomials into its factors, knowing the remainder is a very good start. We can then deal with the quotient at a later time. So let's take a look at another example. We're going to divide this out. Divide f of x equals x cubed plus 4x squared minus 3x minus 5 by x plus 3. We want to know the quotient and remainder, and then confirm the remainder by using the remainder theorem, finding f of negative 3. So let's first do the long division. So again, what we're looking at is what do we multiply x by to get x cubed? That is x squared. We take x squared times everything out front, so we get x cubed plus 3x squared. And then we subtract. X cubed minus x cubed is gone. 4 minus 3 is 1, x squared. Bring down to minus 3x minus 5. We multiply x by to get x squared. That's a positive x. X squared plus 3x. And then we subtract. X squared minus x squared is gone. Negative 3 minus 3 is negative 6x minus 5. What do we multiply x to get negative 6x? Negative 6. We get negative 6x minus 18. Subtracting, we get negative 5 plus 18, which would be a 13. So our quotient, 2 of x, is x squared plus x minus 6. The remainder is 13. We need to confirm the remainder by finding f of negative 3. If f of x is x cubed plus 4x squared minus 3x minus 5, then f of negative 3 would be negative 3 cubed plus 4 times negative 3 squared minus 3 times negative 3 minus 5. Or f of negative 3 would equal negative 3 cubed plus 4 times negative 3 squared minus 3 times negative 3 minus 5. 13. So we have confirmed that the remainder is the same if we use the remainder theorem just by finding f of negative 3. Again, we have no idea what the quotient would be if we didn't actually do the long division. And I agree. Finding the remainder of 13 is a heck of a lot simpler by finding f of negative 3 than it is by doing this long division. So is there an easier way? If it's of the form x minus r, there is. And that is called synthetic division. If a polynomial is divided by x minus r, you can use synthetic division. So let's look at the example. Exact same one we just did. Okay, so take a look here. X cubed plus 4x squared minus 3x minus 5 divided by x plus 3. So let's set up the same way. Okay, now don't do long division. I'm just showing you the setup for long division so you to understand where the numbers are coming from for synthetic. Okay, synthetic division, we're going to make the exact opposite. Instead of going a division bracket, we're going to put a little half box, half bracket, however you want to call it. And what goes in that is the opposite of the number you're dividing by. So if it's x plus 3, you put negative 3 in that little half box. And then beside that, we're going to put all the quotients. So understood 1, 4, a negative 3, and a negative 5. Now, if there was a term missing, we would need to put a spacer in. Okay, you should always have one more coefficient than the degree. The degree of what we have here is 3, x cubed. Okay, so that's degree 3, so we should have 4 coefficients. If you have less than that, then you must have missed some spacers. For instance, if the x squared term was missing, then you would put a 0 in its place. Okay, but it's not, so let me bring that back. This would be synthetic division. Now, here's how synthetic division works. Put a little arrow and a bar. We're going to bring down the first number, 1. And then we're going to take that number times whatever's in the half box. So negative 3 times 1, and place it underneath the next number, negative 3. So negative 3 times 1 is negative 3. And then we add vertically. So 4 plus a negative 3 is 1. Then we take negative 3 times that 1. We get negative 3 again. And then we add. We get negative 6. Take negative 3 times that negative 6 and get positive 18. And we add that. And we get 13, which happens to be our remainder. The exact same remainder we got in the last problem, as you can see right here at the top of the screen. We did the long division. What also we get out of this is the quotient. Okay, these numbers right here are the quotient. They're the coefficients of the quotient. Now, we divided once, so the quotient will be 1 degree less than what we started with. Since we start with x cubed, this will be 1x squared plus 1x minus 6, or cube of x equals x squared plus x minus 6, and we know the remainder is 13. So we got the exact same answer as we did it earlier. Quotient x squared plus x minus 6, remainder of 13. But we did a heck of a lot less work. Multiply and add. Multiply, add, multiply, add. That's it. So if you are of the form x minus r, synthetic division is much, much faster than long division. And it gives you both the quotient and the remainder. Let's take a look at another example. All right, we're going to do this with synthetic division. So let's try to set it up without writing the long division. Do a little half box. What goes in that half box? Okay. Not half. The opposite of that number. So we have a plus 1, we're going to put a minus 1. Now what's being divided? Well, x cubed, so that's our first coefficient. Minus x squared, so minus 1. I don't have an x term, so I have to put a 0 for x, and then a 2 for the number. Again, the degree is 3. So we should have 4 coefficients. You should always have one more than the degree. Bring down the 1. We multiply. Negative 1 times 1 is negative 1. Add. Negative 2. Negative 1 times negative 2 is 2. Add. Negative 1 times 2, negative 2. Add. The remainder is 0. Quotient is x squared minus 2x plus 2. That is very important. When we get a remainder of 0, something special happens. That means that what we divided by goes into that polynomial evenly. There's nothing left. It's a remainder of 0. Okay, so we get two things out of that. That tells us that x plus 1 is a factor and the number, in other words, x equals -1, is an x-intercept on the graph. And that's what the factor theorem tells us. So for a remainder of 0, we're going to know that what we divided by is a factor, and that the number that is in the half box, what would happen if you set the factor equal to 0 and solve, is an x-intercept of the polynomial. So let's go ahead and look at the factor theorem. That's what this is saying. The binomial x minus r is a factor of the polynomial p of x, if and only if p of r, or the remainder, is 0. That's what that means. P of r equals 0, the remainder is 0. And it tells us that x equals r is a 0, you can also say x-intercept of the original polynomial p of x. Again, we get x equals r by taking x minus r equal to 0 and solving. Move the r over, we get x equals r. All right, well, let's practice that. Okay, it says, the next example says divide this cubic, 2x cubed minus 3x squared plus x by x minus 1. State whether the binomial is a factor of the polynomial. Well, it's a factor if the remainder is 0, so let's use synthetic division. 1. It's the opposite of the number we have here. 1. Bring down the coefficients. 2. -3. 1. Okay, we have a small problem. 2, -3, and 1 are the only coefficients that I have. The degree is 3. I should have 4. Where does the fourth one come into play? Well, we don't have a number on the end of it. There's usually a number add or subtracted to it. We have to put a space holder for that number. So we put a 0 on the end. Again, if a term is missing, we must use a space holder. So you must put a 0 on the end. We can now complete this synthetic division. 2 multiplied by the number in a half box is 2. Add vertically. -1. Take that times the number in a half box. -1. Add vertically. 0 times 1 is 0. Add vertically. The remainder is 0. That is big time. That tells us that x minus 1 is a factor of 2x cubed minus 3x squared plus x. Also, it tells us that x equals 1 is an x-intercept of 2x cubed minus 3x squared plus x. Well, we also have a quotient here of 2x squared minus 1. Sorry, x. 2x squared minus 1x. Or we should just say 2x squared minus x. How is that used? Well, the quotient is also a factor of 2x cubed minus 3x squared plus x. Okay, that's also a factor. So we can actually say that 2x cubed minus 3x squared plus x is equal to what we divide it by, x minus 1, times its quotient, 2x squared minus x. And if you notice in our quotient, there is an x we could factor out. We could completely factor this by taking the x out, putting it out front, which leaves us with 2x minus 1. So we have completely factored a cubic. Now that one we may have been able to get away with by originally factoring out an x, but they're not all going to work that way. It's a lot of information for just two little theorems. Remainder theorem really allows you to break things down. This is definitely going to be used in calculus next year. I've already helped a couple of calculus students out that have forgotten about this, so please try to get this into your head and make sure you remember it for next year, because when we're breaking down rational functions, maybe we have a cubic over a cubic, okay? We want to study it the same way we studied it earlier this year with finding vertical asymptotes, finding maybe if something cancels out, which would cause a hole in the graph. All right. Eventually breaking it down to something smaller, we can determine end behaviors, which might be a horizontal, it might be a slant asymptote or something like that. Okay, so this is very useful with all of that. When we get to the higher level polynomials being divided with rational functions. All right, so I think we have one more to look at. We're going to do this one more time. We're going to break it down completely. That's what we're doing. We're breaking down or factoring higher level polynomials, in this case cubics so far. And here's another cubic that we're going to factor. Determine the binomial factors of x cubed minus 7x squared plus 6. And as you can see, this cubic, there's nothing to factor out. The last one we could have factored out an x to begin with, but not here. Also, the thing that's different about this is we're not being told what to divide by. So we have to determine what we should be dividing by. What x values should we be putting into the synthetic division? Well, there's actually a way to do that by hand. It's called the rational root theorem, and we're going to study that in the next section. Right now, I'm just going to show you a little bit easier way, but it does cause you to rely on the graphing calculator. Okay, if you remember, we go back to the factor theorem. I said that x equals r is a 0 or x-intercept of a polynomial. So if we can figure out what the x-intercepts are, we should be able to tell you what the factors are and algebraically prove using synthetic division, hopefully getting a remainder of 0, that those are the factors of the cubic. So we're going to use a graphing calculator to do this. After we know the rational root theorem, we won't have to use a graphing calculator anymore. So let's go ahead and graph this. X to the third minus 7x plus 6. I'm also going to set y2 equal to 0. Okay, the reason why I'm setting y2 equal to 0 is because there's a very easy way to find x-intercepts with a graphing calculator. Okay, and that's using what's called the intersection function. And y equals 0 is putting a line on the x-axis. So when I graph these two, if I can find the intersection of the y sub 1, the graph, with the x-axis, which is what I'm saying y sub 2 equal to 0 is, then we should be able to very quickly and easily find the x-intercepts. So let's go ahead and start with the zoom 6. And we can see there is 1, 2, 3, x-intercepts. Second, trace, which is the calculate menu. Number 5, intersect. Now, we're going to move the x, the blinking spider, whatever you want to call it, dancing spider, blinking x, as close as we can to one of those x-intercepts. And we're going to hit enter 3 times. It's not a left-right thing like we did with max and mins. It's very simple. You pick a first curve, pick a second curve, and hit enter on guess, and it will find it. And it's telling us that x equals -3. Works. And we'll do it again. Second, calculate, trace, intersect. Again, we move the spider over, hit enter 3 times to the next one. X equals 1. And let's see what that last one is. Again, getting close as possible. X equals 2. Now, we're very fortunate here. I will tell you right now, in most cases, you will not get all 3 to be nice. By the way, 3 is the most we could have because the degree of the polynomial we're looking at is 3. That tells us there are 3 complex roots, okay, or 3 complex zeros. All of them are real, and all of them are nice. Usually, you might get 1 nice one, maybe 1 or 2, but usually 1 nice, and the rest are really ugly decimals. And those ugly decimals come from square roots. So we're very fortunate here. We have 3 nice ones. We're not going to use those 3 to break down this polynomial synthetically. So we're going to start with -3. We're going to bring down the coefficients of 1. I have no x squared term, so I have to put a 0 placement. It's -7 and 6. So 1. 1 times the number in a half box, -3, vertically add. -3 times -3 is 9, vertically add. 2 times -3 is -6, 0. That's perfect. Remainder is 0. That tells me that x minus 3, the opposite of that, x plus 3, is a factor of x cubed minus 7x plus 6. Also tells me that x equals -3 is an x-intercept. We already knew that, though. That's how we found this. Okay, so we can move the -3 over, and we can say x plus 3 is a factor. Now, instead of redoing this completely and using the original, why not use the quotient? Okay, so we're going to use the quotient to break this down synthetically. So I'm just going to put another little half box right in front of my quotient. I'm going to put the next number in, 1. And I'm only going to do this to the quotient. The remainder is gone. It's no longer important. So we bring down to 1. 1 times 1 is 1. Negative vertically adding, we get -2. Multiplying, we get -2, and 0. And I'm done. That tells me, okay, since the remainder is 0, okay, that tells me that x minus 1 is a factor of x cubed minus 7x plus 6. And it also tells me what I already knew, that x equals 1 is an x-intercept. So x minus 1 is a factor as well. Now, what we have left, the quotient that's left over, we went from 3 to 2 to 1. The quotient that's left over is actually just x minus 2, which happens to be the factor we get from this x-intercept. Again, when I broke this down earlier, I told you that the quotient is also a factor. So we don't even have to do the synthetic division after we go far enough. Okay? We can simply say that x minus 2 is a factor of x cubed minus 7x plus 6. And we can say that x equals 2 is an x-intercept. Which we already knew. So let's rewrite this. X cubed minus 7x plus 6 is equal to x plus 3 times x minus 1 times x minus 2. Those are the three factors that we found. We completely and totally broke down this cubic. And if we didn't have the calculator to tell us that those work, using the rational root theorem, we could find ones that did work and then prove that synthetically. Or I should say, find possibilities of zeros or x-intercepts that would work. And then once we get ones that gave us a remainder of 0, we could then show that without the use of a graphing calculator. So that's what we're going to do in the next section, is to start breaking these down without the use of the calculator. Again, I like technology. I think it's useful. Probably still going to have you confirm your answer with the graphing calculator. Okay, it's always good to confirm your results. But we are going to show you how to do it without the calculator. That's all I have for you today.